All right, everybody. In advance, if you've not seen me for the past few days, I apologize about the gravelly voice. It is that time of year where my voice goes away. So I'm feeling fine, but if I sound a little bit deeper, a little bit more mysterious today, I'm not trying to phone it in here. We've been talking about carbonyl chemistry, particularly for aldehydes and ketones, and I want to carry on with that. There's two reactions from section 19.7, which I'm going to just reintroduce and then run away from because we have beat those to death recently. And that is the nucleophilic addition of hydrides and Grignards. You know these reactions from alcohols because whenever you add a hydride or a Grignard to a carbonyl, you make an alcohol. So that's why we talked about them previously. So let's talk about hydrides first. If I have an aldehyde and I want to react it, how do I want to do this? I'll give you the reagents, you tell me the product. React it first with sodium borohydride. I won't put a solvent in here, but remember you can use protic solvents, so you can put it in like methanol or I'll write it. I'm telling you, I'm not going to do this, and here I go. I cannot use ethanol or methanol if I use lithium aluminum hydride. I have to follow this up with a second step. We are not always so careful with our ones and our twos. This is a friendly reminder. That's an excellent way to lose 1 point on a quiz or exam is leave off your ones and twos. And when I hand it back to you, you're always like, and I do the same thing. Step 1, add sodium borohydride. Step 2, add acid and water. If these two things are in the flask at the same time, no reaction. This is an aldehyde. What is my product? Oh man, we can name everything. What's the name of this aldehyde? This would be ethanal, but as a common name, does anybody remember the common name of ethanal? Formaldehyde would be if I had a hydrogen over here. This is like an acetyl group, right? Acetaldehyde or acetaldehyde. It's that one that looks like it should be pronounced actaldehyde, but it's not acting out anything. It's acetaldehyde. Acetaldehyde reacts with sodium borohydride to make what product? 1 brownie point if you tell me the functional group, 2 brownie points if you tell me the name of the molecule. It's going to turn into a hydroxyl group and then get protonated. So that would be a add up here. That'll turn that O minus into an OH. That is an alcohol. And what is the name of this alcohol? Ethanol. Today is the first day of Oktoberfest, by the way, for Tolsons who enjoy that sort of thing. Ethanol is a primary alcohol. Go like this. Aldehydes react with sodium borohydride to make primary alcohols. How about ketones? Ketones react with sodium borohydride or lithium aluminum hydride to make what kind of alcohol? Secondary. Very good. I just use sodium borohydride. What's another one I can use? Lithium aluminum hydride, very good. Yeah, I should use some sort of ether here, something aprotic, THF, diethyl ether, those are the common ones. Same thing, second step, follow this up with H3O plus because the hydride is going to add, then I'm going to add a proton to it. What is the name of the alcohol that I'm going to make here? Which one? 2-propanol, or if you want to sound really fancy, isopropanol. Common name, but the way that you'll hear that referred to, also known as rubbing alcohol. 2-propanol. If you're in a hospital system and someone's like, can you give me some rubbing alcohol? You can be like, do you mean 2-propanol? I'm like, get out of here, you annoying little brat. You will technically be correct. Oops. Isopropanol is the name. We said earlier that isopropanol is a secondary alcohol. What was the name of my starting material? This ketone is 2-propanone. What's the common name of 2-propanone? Acetone. 2-propanone is equally right as well. Nobody will call it that. Everybody will call it acetone, but fair game. Everybody remember these? If I take my voice from anything from like a low octave, it just cracks. So I'll just keep doing my smooth jam voice today. All right. Let's talk about adding Grignard reagents. Let me know when this gets weird, by the way. Grignard reagents, we can do the same thing. There's an aldehyde. I can add a Grignard to it. Let's use methyl Grignard just as an easy example. Remember, anything that you see an MgBr attached to, or MgCl, but bromine's most common. Again, we don't want to use protic solvent with Grignard reagents. What kind of product am I going to make? I need to hear from this side of the room. We've had the other side of the room. They're just talkers over there. This is an aldehyde. I'm going to add another carbon to it. Ms. Henson, what am I going to make? Okay. Let me I'll put it in green just so we know where it came from. Next to the alcohol. What's the name of that product? Yep, same molecule, 2-propanol or isopropanol. What? There's multiple ways to make isopropanol. That's crazy. This is a secondary alcohol. Grignards react with aldehydes to make secondary alcohols. There was one carbon attached. I added a carbon to it, so now there are 2 carbons attached. What's the product of acetone with methyl Grignard? A tertiary alcohol. Which one, Aiden? What is it? Isobutanol? Let's draw it out. So add another carbon to that. We turned a ketone into a tertiary alcohol. Excuse me. Which tertiary alcohol? Not isobutanol, but tert butanol. We'll walk down memory lane from literally the previous chapter. I need everybody to nod your head at me that this looks familiar. Okay. Did I show you the mechanisms here? No. Do you need to know the mechanisms? Yes, you do. Do you know the mechanisms? Hells yes, you do. Hex yes, you do. Darn recording. You can get away with anything these days. Bless you. Any questions? Okay. You know 19.7. Let me show you something you don't know. 19.8. The nucleophilic addition of amines. Nucleophilic addition of amines is going to drive you a little crazy because they make a whole bunch of things that sound very similar with vowels changing at the beginning. Amines are going to form imines and enamines, if you know what I mean. That's right. I've been thinking about that joke all morning long. It landed perfectly. I can tell that I was like, just right. Amines react with aldehydes and ketones to make amines and enamines. Students always have a hard time with this, and today is not great with my voice being that way, but let's practice saying these words. This one is amine. Amine. I'm sorry, one more time. Amine. Good. This one is imine. One more time. Imine. Fantastic. And the hardest of them, enamine. Enamine. This one always sounds like sea anemone to me. Enamine. Let me show you what I intend to show you for this. I didn't do it that time. I do have this much self-control. All right, here is a test model or a test molecule. Let's draw these out, put it nice and big. I'm intentionally leaving a hydrogen in there because it matters what type of amine I'm using when I react it with, in this case, a ketone. But these reactions work for aldehydes as well. This can be a ketone or an aldehyde. All right, if the nitrogen that I'm adding to this has one carbon on it, that is, it's an NH2, so there's one carbon attached here, that is called a primary amine. Now, this is a little bit different than how we think about alcohols. When I refer to a primary alcohol, I'm saying that the carbon bearing the OH has one other carbon attached to it. When we talk about primary, secondary, and tertiary amines, it's how many carbons are attached to the nitrogen. So this nitrogen has one carbon attached, and that's why I call it a primary amine. A secondary amine is one that has two carbons attached to it. So that would be an NH with two carbons attached to it. The nitrogen is now a secondary amine. The reason we can get away with this is oxygen only ever makes one bond. So I can't talk about the oxygen having multiple carbons. It's always going to have one carbon attached to it if it's an alcohol. Amines, on the other hand, can be primary, secondary, tertiary, and quaternary. So everybody see the difference there? I've got you trained hopefully pretty well to say, ooh, primary alcohol. When I say ethanol, you're looking at that carbon. When I say primary amine, you're looking at the nitrogen. So I need you to be able to switch in there. Okay, when you have a primary amine, and these happen under acidic conditions, and I should really keep this above the arrow so it's not confusing. Both of these are acid catalyzed. You are going to replace the carbon oxygen double bond with a carbon nitrogen double bond. This molecule is called an imine. It has come to my attention that some people, especially in Oklahoma, take advantage of our Southern draw to differentiate these. And I am here to say that it's not correct. They say amines, imines, and enamines. It is amine, imine, enamine. I will go to my grave on that one. If it is helpful for you to think of it as imine, fine. It's wrong, but fine. This is an imine. An imine you'll hear about in biochemistry as well. One of you is in biochem. Is anybody else in biochem? What do you call imines in biochemistry? How many says amine? Biochemists will often refer to this as a Schiff base. You heard Schiff base? That is really a biochemistry term. Schiff was a biochemist. There's a lot of nitrogen catalysts out there, and they make these imines as intermediates. And so we talk about them as Schiff bases when it's used in a biochemical catalytic pathway. You won't hear me call it a Schiff base, though. You hear me call it an imine. And I love that. Is it Dr. Kim? I love that Dr. Kim calls them amines as well. I knew he was a good guy. Okay. Carbonyl turns into carbon nitrogen double bond. That should look pretty weird to you. When I first saw this, I was like, ugh, not a fan. If you have two carbons attached on the nitrogen, you're going to make this thing. Let's put our lone pairs on here. This molecule has an alkene and an amine, and so we lovingly refer to that as an alkene amine, or shorten it enamine. And I should note, both of these reactions lose water. And notice I gave you reversible arrows. How do you think you turned an imine back into a ketone or aldehyde? Add water, right? And typically under acidic conditions, you can do it under basic conditions, but you can turn an imine or enamine back into a ketone or aldehyde by adding water. You want to make the imine or enamine, you need to remove water from the system. Are you guys emotionally and mentally ready to see how we turn a ketone or aldehyde into an imine? Fair warning, it's under acidic conditions. And remember, as I've been preaching for a while, acidic conditions are a pain in the butt. Mainly because there's so many steps of adding or removing a proton. So I'm going to get done drawing this mechanism and you're going to go, oh, because there's like a bunch of steps to it. But keep in mind, there's actually like two key steps where something's going to add or something's going to remove. Everything else is a proton transfer. Let's do this thing. It's going to be great. I'm going to use a more simple system. We use just acetone to start here. We're working under acidic conditions. So what's the first thing I should do? Protonate something, right? Add an acid. And I need to protonate something. What's a good thing to protonate in my system? Oxygen's got lone pairs. Let's give the oxygen a proton. This makes my activated carbonyl. Next step, my nitrogen is going to come in and attack this thing. I'll use methylamine. And let me draw the CH3 out there just so you can keep track of it. Again, if you're a Breaking Bad fan, I think I brought this molecule up before. Methylamine is the star of one of the later episodes in the season. This is used as a precursor to make methamphetamine. It also smells really bad. Low molecular weight amines smell like cat pee. So not something you really want to work with very much. The nitrogen is nucleophilic. The carbonyl carbon is electrophilic. So we're going to draw an arrow from the nucleophile to the electrophile. What's that going to make? A tetrahedral intermediate. Because Dr. Green did that weird thing where he like snaps, makes a big deal out of it. Down here, I have a nitrogen with the hydrogen and the CH3. Oops, 2 hydrogens. So everybody's still attached. When that did the attack, leave everybody on there. Some students get eager beaver and they try to drop protons. In order to make this a little bit easier, I'm going to use a trick that your book uses. Instead of drawing the mechanism for this, the nitrogen is going to lose a proton. The oxygen is going to gain a proton. I'm not going to draw arrows for it, because if I just draw this next structure, I think you guys can use your imagination. About how that occurred. Am I blowing anybody's mind with that step? Can you see it? You see it okay? A base is going to come in and take this proton, push the electrons onto the nitrogen, so it lost a proton. This is going to take a proton from the environment. So it had 2 lone pairs in the oxygen. Now it's got 1 lone pair and another hydrogen. I just saved us from drawing 2 steps of a mechanism. I can do it. Give me some feedback here. Okay, I'm going to show you in 1 step how it would work. A base would come and take that. Now I lost a proton down here. This is going to pick up a proton from the atmosphere. This is going to happen in 2 steps. It won't occur simultaneously. This thing, well, never mind. Okay, so added a proton, did an actual reaction, added and lost protons. I told you I kicked off water. This is kind of looking like water, yeah? How can I get that to go away? No, it's already protonated. I need to break this bond. And so if I break this bond and I push it onto oxygen, that'll turn this thing into water. Now, if I do that, I'm going to make this carbon down here not have an octet. This carbon will be a carbocation. Do I have anything that can help out with that carbocation that would form? Lone pair on the nitrogen can get involved. So we're going to push that down to make a carbon-nitrogen double bond, and that will kick off water. Lone pair is now a double bond over there, which means this nitrogen now has a positive charge. This ion has one of the cutest possible names, I think, that we can get for it. So this is like an imine, but it has a positive charge. And remember, when we have positive charges, we call them ium with the suffix. So this is iminium. Aw. If you have a small dog, I think iminium is like the perfect name for that small, like a purse dog, you know, the real yippy bitey kind. Iminium. You could call it Mini or Emmy. Emmy? No, you don't like it. We don't like small dogs, or we don't like the name. Oh. Well, that's why you could just do Emmy or Emine if you want to do a short note. I don't like any of those. There. Iminium is not the final product. Dying. I need to lose a proton. Excuse me. Got too excited about aminium. This will turn our aminium into an amine. Lots of squinting at the screen. In advance, I told you the mechanism looks really spooky, but there's really only kind of two main things that happen here. The nitrogen added to the carbon, and then the nitrogen kicked off the water. Those two steps are the main things: addition, elimination. Otherwise, everything else is just a proton transfer. So if you can start to break your mechanisms down into, am I adding or removing a proton? That's a common thing we do. There's only two other things that really occur here. There's like 6 proton transfers though. So that's how you form an imine. To make an enamine, we're going to do this entire pathway plus some. I'm going to spare you from redrawing this whole thing. So what I'm going to do is draw this up to the aminium ion, but instead of having 1 carbon on here, there's going to be 2 carbons on here. An aminium ion with a secondary amine means that there's no proton here. Right. So when I had an aminium, I took a proton from it and I made the imine for the final molecule. If this is another carbon, let's say another methyl group, then I can't take that proton to make this nitrogen neutral. So what can I do? We'll use acetone and dimethylamine. And under acidic conditions, I'm going to jump forward to that aminium ion I would form here, right? So this would protonate, nitrogen would attack, tetrahedral intermediate, protons change hands, nitrogen kicks off the water. Then we're left with this guy. Just to emphasize that I skipped several steps here. Let's just say that lots of things happened to get me here. This is my aminium ion. All right, I have a nitrogen with a positive charge. Nitrogen's pretty electronegative. It does not want to have a positive charge. Previously, I pulled a proton off of this to give it a lone pair, and that's how I made it neutral. I don't have that option here now. So how can I get this nitrogen a lone pair to make it not positive anymore? What's that? You're right. Yeah, I got a double bond here, right? And I can push the electrons up onto the nitrogen and give that nitrogen a lone pair. If I do that, I'm going to steal from this carbon, and then the carbon's going to have a positive charge. That's not a great bet because this nitrogen's positive, but it has an octet. So how can I get rid of that positive charge but keep everybody happy? We could pick off a sick buffalo from the edge of the herd. All right, let's do an elimination reaction. The base, and I'm just using generic base here. This can be water. These protons are very acidic. Is going to come take a proton from the edge of the molecule. Now, it seems funny that the base would react with this, but once this nitrogen becomes positively charged, those protons become very acidic, because this is kind of an allyl unit, right? It's a double bond next to a single bond. So that this hydrogen is electronically connected to that nitrogen. If you don't believe me, which you totally should, you can push the carbon-hydrogen bond to a carbon-carbon bond, and then push the carbon-nitrogen bond onto the nitrogen. That's how we're going to get our nitrogen to be neutral. That's where that lone pair came from. And that's where that double bond comes from. So we turned our iminium ion into our alkene amine. Do me and yourself a solid favor. And this weekend, I want you to get a few blank pieces of paper, or preferably a whiteboard if you want to not be so wasteful. And I want you to write this mechanism down over and over and over until it becomes comfortable. The enamine and iminium ion, or imine and enamine formation, are very similar to a bunch of other reactions under acidic conditions. It's very difficult. It looks weird, but it'll be something that you'll see quite a bit. So if you can get this mechanism to where it doesn't feel so awful, because I know it feels awful right now. I remember distinctly learning this. Like, this was the moment in OChem 2 when I was like, hey, I kind of like this class. And then we got to this part and I was like, no, this is not for me. Get this mechanism down and a bunch of other things will be more familiar afterwards. Let me show you a reaction that I'm not going to ask you to know the mechanism for. Because if I ask you to do one more mechanism, you probably quit on me right now. You just walk out. This is the Wolff-Kishner reduction. Wolff-Kishner reduction is pretty cool because it can turn a ketone or an aldehyde into an alkane. So, for instance, I can turn that ketone just goes away, 1, 2, 3 carbons into a alkyl group. It's attached here. And the reagent for this is total bad A. H2N NH2. This molecule is called hydrazine. Has anybody ever heard of hydrazine? No? I don't know why this is going down. Hold on, let's get the other way. Hydrazine is rocket fuel. It's used in rocket fuel. If you like watching blast offs and wondering how they get so much fire to come out of the bottom of these things, right? Like I have a fireplace, I put wood in there. I can get a roaring fire, but not like, that's like fire, right? Like, what do you kids say these days? Fire, right? There's a lot of heat coming out of the bottom of those things. How do you get that to happen? You put in not only a fuel source, but something to increase the oxidation rate. So you add oxidizers. Hydrazine is a common oxidizer added to rocket fuel to make it go boom a lot faster than if you just say lit gasoline on fire. In our case, you can also use hydrazine in the presence of base, KOH, to turn our carbonyl group into nitrogen, into gas, and water. Pretty nifty little reaction. The mechanism is straight up crazy town, so we'll skip it for now. But I do want you to be familiar with adding hydrazine to carbonyl compounds. It doesn't have to be benzylic. You can have any carbonyl will turn into the carbonyl. Basically, when you see hydrazine and KOH, you go over to your carbonyl and go, it's not there anymore. You can do that? Let's do it. What are my major products for each of those reactions? Any takers? What's that? One is, which one's butane, left or right? One on the right is butane, correct. So we did Wolff-Kishner reduction, just get rid of that carbonyl, butane. Now that's a super boring thing, right? You took, what is this molecule? You took 2-butanone and all its chlorate, it's got a functional group, it's super cool. You turned it into butane. That's kind of lame, right? There's easier ways of getting butane. Get oil, boil it, take the butane off, good to go. But if you need to, you have options. Anybody do this one? It is an enamine, very good. The enamine here is from this secondary amine. What I do when I see these is if I go over here and classify, that is a secondary amine. And then I remember back to all the pain I learned the mechanism from, but you don't actually need to know the mechanism. You can remember that the oxygen goes away and in its place, I'm going to add a nitrogen. Now I can't put another double bond here because if I do, the nitrogen will have a positive charge. So I need to add the double bond somewhere else. Where should I put that double bond? Zaitsev. Should I put it here or should I put it there? Why? Zaitsev's rule, right? The more substituted alkene, very good, is formed. So that is going to be the preferential enamine that I would make. See, it's not so bad. You guys are smarties. All right, one more, and I need the whole page for this, so I got to erase this thing. Remember when we had alcohols and they were causing all sorts of problems because the acidic proton wouldn't let me run a reaction I wanted to. So I masked the alcohol and I ran the reaction I wanted and then I unmasked it. What's that called? When you cover up a functional group and then uncover it later on. What's that? Protection. Yeah, protection chemistry. There is a protection type of chemistry for aldehydes and ketones as well. These are called acetals. Let's do this one as well, because this word doesn't look like it should be pronounced that way. Acetal. There you go. You got to really cuss through it.
How do you spell acetyl?
Acetyl, YL. You're like, what? What sort of crap am I pitching up here? Acetal formation are carbonyl protecting groups. All right, you can take a ketone, add to it excess alcohol. So we need at least two. Well, I'll show you. We need excess alcohol in the presence of an acid catalyst. And that is going to form a diether. So wherever my carbonyl is, I'm going to have two ethers hanging off of this. This is called an acetal. This reaction is reversible. Guess what other product we give off here? Water. Guess how you get this reaction to go backwards? Add water and acid. Guess what this mechanism looks really similar to? Amines. Yay. On the recording, you can't hear it, but everybody said, how does that reaction work? I need to see the mechanism. Of course, I'm going to show you the mechanism. Step one, this thing's going to take a proton. Because under acidic mechanisms, what else would you do except for add a proton? And in particular, let's add the proton to the carbonyl carbon, carbonyl oxygen. What's the next step? When I did this with amines, the next step was for the amine to attack that activated carbonyl. I don't have an amine anymore. Now I have methanol. But if you squint real hard, you can kind of pretend like the oxygen is a nitrogen. So the oxygen is going to attack that carbonyl, push the electrons on top, and make a tetrahedral intermediate. I can't draw it all fun like I normally do because it's all over the place now. Got a positive charge on this oxygen. The other oxygen is neutral. Here I am going to take some liberties with my adding and removing protons. So without showing you arrows, a base is going to take a proton from this oxygen. This is going to take a proton from something else. The reason I'm doing that is, let me put my positive charge closer to the oxygen. The reason I'm doing that is I'm trying to get this thing to look like water. I need that to go away. I did. I took this bond away. So it's neutral. I added a bond to this one. Oh, I did. I made it benzene. It's not benzene. Thank you. Just making sure you're paying attention. I thought the mechanism wasn't hard enough, so I thought I'd mess with you a little bit. Gabby appreciated it. Gabby, what's my next step? This kind of looks like water, right? That needs to be kicked off. If I kick that off, that carbon's going to have a positive charge. I don't like that. So what can I do? Take it from somewhere else. That oxygen's got lone pairs. They can push down to make a new bond over there. And so I just lost water in this molecule. Now, I know this doesn't look familiar to you because the iminium ion mechanism or the imine mechanism isn't familiar to you. But again, if you get that mechanism down and you go back and look at this one, it's going to feel very familiar up to this point. All right, from here, take a look at this guy and look at that guy. Pretty similar looking to each other, right? That one's got a proton on it. This one's got a CH3, but otherwise they have carbonyls with oxygens with positive charges. I'm going to go through this process again. Right? I added methanol to this molecule. I'm going to add a methanol to this molecule. Oxygen is going to attack that carbonyl, push the electrons up there. You know what? Oh, okay, I'll leave it. How do I turn that molecule into this one? Base. I need to take a proton from that. That would have looked a whole lot cleaner if I would have gone up at this point. Did not plan ahead. Let me show you how you can use this reaction as a protecting group. Sorry, I know I see Penn still writing, but just so I don't rush us too much at the end here. What I'm going to do is use this chemistry in a synthesis. Let's say I wanted to turn this molecule that has an ester and a carbonyl and a ketone into a molecule that has a carbonyl and an OH. What kind of reagent turns my ester into a primary alcohol? Okay. Jones goes the opposite way. Turns this primary alcohol into a carboxylic acid. I need to reduce this molecule. So I could use lithium aluminum hydride to turn my ester into a primary alcohol. If I added lithium aluminum hydride to this, I would reduce both the ester and the ketone, right? I didn't reduce the ketone, which means I need to mask the ketone. This can't be done directly. So instead, what I'm going to do is protect my ketone. I'm going to show you a really slick reagent for this, where the alcohols are built into one molecule. We've talked about this molecule before, I believe, called ethylene glycol, the one that you don't want your pets to drink. Ethylene glycol has both alcohols built into it, which means I can turn my carbonyl into an acetal. It kind of looks like a bug. I think this looks like a praying mantis face, personally. This is my acetal, my protected ketone. I can then run the reaction that I want to run. Lithium aluminum hydride. Oops. H3O plus. That reduces my ester to a primary alcohol. My acetal group is still hanging on there. I can then unprotect my alcohol using H3O plus and heat. So I could do that over here as well. I'm showing it to you as a second step or as a separate step, just so you get used to seeing it that way. That turns my protected alcohol into a deprotected alcohol. So this is my protection step. This is a deprotection step. I can't just add lithium aluminum hydride. It would wreak havoc on both sides of this molecule. I can mask my ketone, run the reaction I want, and then unmask the ketone later on so that it only reacted half that molecule. Should you have not had enough organic chemistry, and I can tell that's most of you, you need like 50 more minutes of organic chemistry. Come see me in Action Center from 11 to 11:50. No, 10 to 10:50 right now. Otherwise, have a great weekend and I'll see you on Monday.